Awesome. And we can get started. And if anybody else joins while we're going, it's their loss for being late, and they can learn an evolutionary lesson about being late to seminar group events. But Kaiyu, thank you so much for joining us today. I'm really excited about this talk, uh, and this has been requested, I think, for a while. So it's exciting for me that we managed to get you. Um, we're sort of an interesting group in which there's people who do machine learning. There are people who do formal methods. There are a couple people like Daniel Melser who do both. But increasingly, that intersection is like of very broad interest and not just of niche academic interest. And you're one of the people, I think, at the forefront of that. So we're really excited you were willing and able to come talk to us today. So with that, the floor is yours. Thank you so much for joining us.
Yes, thanks for the introduction. So I'm Kaiyu, and I'm a research scientist at Meta, and I'm in the New York office. I think this is a very exciting time to talk about this, because amid all those news about IMO and other stuff. So I'm going to talk about formal reasoning and language models for AI for mathematics and verification. So we're kind of now in a like AI arm race, especially in math and coding. So whenever you see a new model like OpenAI or other frontier lab release, they have kind of have a figure like this where they highlight the model's performance on benchmarks on mathematics and coding, like the AMY exam and also the Math Vista dataset here. And here they include the AP calculus. Like similar for other places like Gemini or Grok from XAI. Um, and like last year, or maybe it's the year before last year, XTX Markets has this AI challenge that's $10 million for, I mean, if you can develop an AI that can win IMO, and you're, well, an open AI system that can win the IMO, which means you have to release the all the code. So this year's IMO winner don't qualify. Um, and then last year, Google released or announced they have achieved the silver medal level with the alpha proof system. And this year, just a couple of weeks ago, we have four claimed IMO gold medalists for AI. Two of them it's informal, just a language model, like one from OpenAI and one from the Google DeepMind. And the other two claim to have used formal methods, in particular Lean. One is the Harmonic, which is a startup in Palo Alto, and the other is a ByteDance, like kind of like a Meta in China. Um, so the progress is pretty fast. We well for the silver medal and gold medal level AI, well they only exist in blogs and tweets, so we don't know much about how they work internally. I think there are. Well, ByteDance recently actually released a technical report, so but it's relatively high level. So I think it's the status is you kind of you know what are the ingredients. Like you know there's a theorem prover and there are some way they generate data, but there's no easy way to for you to actually use it. And even beyond the competition math, people are also looking at can we do more frontier mathematics, like research level mathematics. So this frontier math data set released by Epoch AI, um, when it was released, people thought, okay, it's too challenging to get even a non-zero score. But only a few months after, OpenAI O3 get pretty high, or at least non-trivial, on this frontier math data set. So one question is why math and coding? So I would say people are interested in, especially big language model labs are interested in math and coding for at least a few reasons. One is math and coding it requires complex reasoning and planning, so it's a very good proxy for if we want to build language models that are good at reasoning. Um, also, if you can, I think the assumption here is if you solve reasoning, you will unlock a lot of applications. Like you want language models to maybe schedule travel for you or manage your calendar. then you need reasoning, and you use mathematics as a playground for reasoning. And also, mathematics is relatively easy to evaluate. Well, because you have a problem and you have an answer, you can just check if the model's answer is correct. Actually, it's more tricky than that, especially when it comes to proofs, but that we will cover later. So if you compare mathematics with like writing a crime fiction or like composing a symphony, arguably a crime fiction and symphony also requires complex reasoning and planning, but there's really no good way to evaluate how good your AI generated fiction is, unlike mathematics. So then we know why people are think mathematics is important for language models. Then the next question is, how do we train language models to solve mathematics? So here is a very simplified view. So we have two classes of methods, supervised fine-tuning and reinforcement learning for training language models for math. And I will go through very briefly each of them. But as you will see, for supervised learning, for both supervised learning and reinforcement learning, it seems that good data and verifiability is the key. So first, supervised learning. So you have a language model that's pre-trained on internet scale data sets, mostly text and sometimes also code. So the first thing you do is you want to add some mathematics. So you collect a lot of math-related documents from the web. And I see people in typing in the chat, but I cannot read.
Oh, sorry, Kaiyu. I was just asking, I thought maybe an audience member would know, but I'll ask you instead. Are all the benchmarks you mentioned with the theorem prover? Because I would think otherwise it'd be too labor intensive to check the proofs.
You mean the benchmarks here?
Yeah, exactly. Yeah.
Those are not theorem provers. They are questions that has a numerical answer, so that you can always check if the answer is correct.
But in
And
that case, the flavor is different, right? Because it's not a proof. So it's
yeah,
like,
and it's usually lower level, like
right.
elementary school or low level middle
Okay.
school. Yeah.
Okay, cool.
When
Thank
when you come to IMO or even more advanced math, it's almost always proofs. Um, so first you get a lot of, I mean, but feel free to interrupt anytime, but I cannot see the text in the chat. Um, so you do like continue pre-training using like math specific web documents. So those can from like archive or math overflow or other sources as long as they're related to math. So then you get this base math language model. And then you want to teach the model how to generate well-formed solutions. So here you collect a smaller but higher quality data set. This data set has problems and with like step-by-step detailed solutions. And so here you train the model to predict the solution given the problem. And you get a fine-tuned math language model. And the other thing you could do but that's entirely optional, is you fine-tune the model further on another data set with what they call tool integrated solutions. So we will see it in 1 second. So this is an example. Here tools basically means like external tools like Python. You can call SymPy or other tools, libraries in Python. So you have a problem statement here, and you want the model to generate the solution. The solution has both reasoning in natural language, and it can also call external tools like Python. And at the end of the solution, you have a final answer that's in the box. So if the model outputs the answer, you can extract it and compare with the ground truth.
So
Here,
I
as you
have a
see,
question.
Mhm.
So does the LLM from the English statement of the problem that is stated, like for instance, sum of the two squares, they're able
uh,
to sort of understand and write down a Python code that we are talking about x square, y square, and all that.
yeah, because the model has already been pre-trained on text and code, so has the understanding of,
Understanding
yeah.
basically.
But you
So
want to
if we are
enhance.
ambiguous over here, ki like they're n square, if we rather not talk about say squares and complex numbers, if we give them the Fermat's last theorem, so will it
Mhm.
also try to solve it with SymPy, but not understanding that n is variable and all that kind of stuff?
Well, famous last theorem is a bit different because it's a theorem proving problem. It's not
Okay,
having
okay.
sympathy.
I know. I just wanted to know whether I don't want it to solve, but I wanted to know if it could generate the Python equivalent for the Fermat's last theorem also, because in that case, you're talking about n being an arbitrary number and all that kind of stuff.
Uh, um, but in that case, well, it can here there's no constraint. It can generate anything, but well, there's
Okay, okay.
no guarantee that thing will actually solve your best problem. But here it's you are limited in a case where the final answer is a number, so that you can compare. But we will talk more about theorem proving in the later stage. Um, so here, the key is actually in this pipeline is the data set. So you collect a lot of data sets, I mean, with various sizes and various quality on mathematical problems and their solutions. But once you have the data set, the algorithm for training the model is very straightforward. Um, so what data set do we have? So currently, the largest publicly available data set for this purpose is the Numin mass data set, which is about 900K example. Well, that's a modest size, but it's not huge, well, considering how data-hungry language models are. And okay, the other, then we can think about what if we since we don't have enough data, what if we have only the final answer but not the intermediate steps? Because the more expensive data is the data that has intermediate steps. So if we can learn from only the final answer, if we don't need the intermediate steps, then that potentially can solve the data bottleneck. So here is how where reinforcement learning comes in. So this using reinforcement learning to solve math reasoning problem has become, well, quite popular recently. And it relies on the fact that the problem is verifiable, which means you can just compare the number. And so here's a high-level view of how it works. You have a problem statement. You give the problem statement to the model. The model will output something that's not guaranteed to be correct. And well, if in this case it is correct, then you give it a positive reward. But in other cases, maybe the solution is not correct, or even the solution is not is ill-formed. You cannot extract the solution. Then in this case, you give a reward 0. Then you just apply reinforcement learning to maximize the expected reward. That's the probability of generating it's positively correlated with the probability of generating correct answers. And there are a range of reinforcement learning algorithms you can use to do this optimization. And currently, the most popular choice is the GRPO algorithm that's popularized by DeepSeek R1. Well, just to show how popular, well, how much momentum this method has, not long after this paradigm became popular, the ACM Turing Awards was given to the two pioneers in reinforcement learning. Um, so, but here this method also has a problem. That's the solution must be verifiable. Because if it's not verifiable, there's no way to assign the reward, and then there's no way to do reinforcement learning. So that's not applicable to proofs. So if the problem is to prove something, then there's no easy way to check if the proof is correct or not. So that's what we're going to solve in the rest of this talk. So just to recap what we have right now, we have two classes of methods to do math, to teach models to do math: supervised fine-tuning and reinforcement learning. For supervised fine-tuning, you need a lot of good data set. That's expensive to collect. And for reinforcement learning, you need the problem to be verifiable. And most state-of-the-art language models on math, they are these two key ingredients, but combined with very strong, very big model and very good engineering practice. So the question is that enough for AI to solve mathematics? Well, of course, we know the answer is no. There are a few gaps. One gap is we currently models are doing very well on pre-college math, but struggle with advanced math. So here's a quote from Terry Tao, one of the best mathematicians right now. And so he tried ChatGPT to do his research problem, and he concluded it's still struggling with the most advanced research mathematical tasks. So you may ask, didn't we talk about OpenAI o3 on frontier math benchmark? Isn't it already doing well, very good? Yes, but the catch about frontier math benchmark is it's very advanced math indeed, but the problems are selected in a way that they must have numerical answer. So that's not typical for advanced math because like proofs are by far more typical. So it may be the case that language models are quite good at deriving the answer, although quite difficult at generating rigorous intermediate steps. So that's related to the second gap. So here are the results from Putnam exam and also the US AMO exam. People have manually examined their results generated by the model, and they find that the models are generating the answer right, but failed to generate the valid proofs. I have to mention that this thing may be changing right now because the recent IMO results, that's verified by humans, and well, they must be rigorous to a certain extent. Although currently we don't have details, it is quite possible that although the model do not use formal reasoning directly, but maybe under the hood it's trained on data sets generated by formal reasoning. So here we show an example of language models generate invalid proofs. So here's a theorem. You have ABC that's greater than 0, and there are A times B times C equals to 1. And you want to prove this inequality. And you give it to a model. The model apply, so step 1, apply the AMGM inequality. That makes sense. But if you look at the red box here, it's essentially the model is trying to multiply an inequality by a positive constant, which shouldn't change the inequality sign. But here it flipped the inequality sign. So this kind of error is very easy to find out. Well, not very easy to find out. It's very easy to check once someone pointed out. But if you have a model generates a very long proof, it's very difficult to identify them. So then we believe language models alone are not enough for solving mathematics. So because two reasons. So one is data scarcity. So language models are kind of limited to data-rich domains like pre-college math. But if you want to use them to do advanced mathematics, by the definition of advanced mathematics or mathematical research, you don't have a lot of data. It's very unlikely that you will search the internet and find a solution to your research math problem. And also there's a lack of verifiability because the proofs cannot be verified, and therefore you cannot provide learning signal for the model to learn, or you cannot even evaluate how good the model is. So if language models are not enough, what else do we need? Here, we're going to argue that the missing ingredient is formal reasoning. And the future is you will integrate informal reasoning of language models with formal grounding in systems like Ling or Coq. So here, by formal system, we mean a range of things. Like, well, it could be first or higher order logic or dependent type theory, or even computer programs and their formal specifications. But later in this talk, when we dive into concrete projects, we will be mostly working on Ling. So here, it's a very brief introduction of what Ling is. So Ling, there's a class of tools called proof assistants or interactive theorem prover, and Ling is one example of proof assistants. there are other popular examples like Coq or Isabel. For the purpose of this talk, any of them, well, they are very similar to, for the purpose of using AI to prove theorems, although they are based on different logical foundations. Well, then for Ling, you can think of it as a programming language for writing formal math and so, not only software, but also math definitions and theorems and proofs. And here's the example. You define natural numbers as either 0 or, well, another natural number plus 1. And once you define the natural number, you define the addition as a recursive function between two natural numbers. And once you define the addition, you can state a few theorems about addition, like a plus b always equals to b plus a. And then once you state the theorem, you can write the proofs. So, and here is only one file in Ling. And so in this file, in the theorem, when you execute the proofs, it implicitly gives you a proof tree. In this tree, you can think about the root node as the initial state. That's the theorem you want to prove. And the leaf nodes are states that are already solved. And the edge in this tree is what we call tactic, or you can think of a tactic as a step in the proof. So then the theorem proving is you start from the root node and you use tactics to expand the nodes until you reach a leaf node. And here is only one file, and you can have many files in a project, and projects can be, well, just like software projects. These math projects can also be open sourced on GitHub and reused by other projects. Like if you define real number and prove something about real number, maybe another person can do real analysis or PDE on top of your definition. So then, so here's the roadmap for the rest of this talk. We want to do AI for formal mathematics, and there are a few things we mean by AI for mathematics. So one task is theorem proving. So here the input is a theorem statement in Ling, and the output is a proof in Ling. And the correctness of the proof can be checked by Ling. So the goal is not to generate any ground truth proof. So it's okay as long as your model can generate any proof that can pass the Ling checker. And another task is auto-formalization. So here on the left, we have informal math. That's human written math in like textbooks or papers in natural language. And we want our model to translate them into formal math in Ling. So we will start with theorem proving. So here is a very typical architecture for theorem prover. It's a combination of proof search and tactic generation. So at the beginning, you have a proof state, like that's the theorem you want to prove. And then you use your language model to generate the next step. And you can use it to generate multiple potential next step because you don't know which one is the correct one. Let's say you get 3 potential next steps, and then you can run them separately in Ling, which brings you to the next state. And then you can do that repeatedly, generating new steps on new states. So that implicitly gives you a tree. And the goal of theorem proving is to find a path in this tree from the root node to a solved node. And that path corresponds to a proof. And so here is the architecture for tactic generation at each step. At this particular step, you have a goal, that's the current statement you want to prove. And the model also has access to a formal library that's potentially the lemmas you can use. And it outputs the next tactic. And so I'd like to say this architecture is very common, but recently there are also people trying to generate the entire proof in one shot instead of generating only the next step. And this kind of whole proof generation is becoming increasingly popular. So, and actually, this idea is not new. It's there before language models, and it's even there before Ling. So here are some classical papers on using more classic machine learning algorithm like KNN or even SVM to generate the next proof steps. But what's new after we have language models is, unlike classic machine learning algorithms, language models are pre-trained on existing mathematics, and it can learn mathematics during pre-training. That's why, so that mathematical knowledge will be useful for guiding the proofs. Mm, then we will dive into a particular project called Lindojo that's a while ago, and it's actually the first language model-based theorem prover that's open sourced and you can use. It provides the dataset extracted from Ling for training the language model and also for evaluating the language model. And we also released the trained model checkpoints as long as the tools for extracting data and interacting with Ling. And here's how Lindojo works at a high level. So you have Ling, you have like Mathlib and other library written in Ling that's on GitHub. You can use Lindojo to process those repos written in Ling, which will give you a dataset. Here we process Mathlib, which gives us about 100K theorems with proofs that's written by human. And they contain about 200K tactics. And those tactics make use of a bunch of premises or lemmas. And once you have this dataset, you train a machine learning model on this dataset. And once you have the model can interact with Ling programmatically to prove theorems. And so that's our dataset. And what we also propose a model called retrieval augmented prover or reprover. And so here the motivation is, if you only train the model to predict the next step given the current state, the model has no knowledge of what existing lemmas are there. But when doing mathematics, you almost never start from scratch. You build on top of existing lemmas. So here we want the model to retrieve lemmas from a library and can use those lemmas to predict the next steps. And here's the input for the model. You have a current state that's the theorem you want to prove. And you have a library that's all accessible lemmas in the library. That's about 33K for an average theorem. And the first thing you do is you encode everything into vectors. So the state will become a vector, and each lemma will become a vector. And then in order to know which lemmas are useful, you multiply the state vector with all lemma vector. So then for each lemma, you have a score, that's a scalar. And then you pick the lemmas, the top lemmas with highest scores. Say you retrieve a bunch of lemmas, and then you combine the retrieved lemmas with the current state, and you use another language model to generate the next tactic. And here the model basically have two parts, one the retrieval part and the tactic generation part, and they are trained separately. And so that's our model. And recently there are a bunch of work building on top of this or trying to improve this architecture or trying to do whole proof generation instead of just generating the next tactic. Like a DeepSeek prover, from DeepSeek, and also the most recent one, Gödel prover V2. That's the best open source provers we have right now. And the most powerful prover is probably Seed prover. They claimed gold medal this year, but they're not open sourced, but you can read the technical report. But well, conceptually they are very similar to the model we introduced here, but they also put a lot of effort on synthesizing a larger data set. And so here is the Gödel prover V1. I probably should update this, but and I think the story remains the same for V2. is that you can synthesize more theorem statement by auto-formalization. That's you using language model to translate mathematics into formal math, and then you use the result to train the model. And a particular technique used here is called expert iteration. That's you train a prover. The prover may not be very good, but you use the prover to prove theorems. Well, even though it's not good, it must be able to prove at least some theorems. And then you add the new proofs into your training set, then you get more proofs. And then you use this bigger data set to retrain the prover, and you can iterate for a few iterations. And here in the figure, the x-axis is the iteration and the y-axis is the performance. You see, as you do more iterations, the performance generally improves. Okay, so that's the theorem proving part. And here is the limitation of this approach. Still, language models works really well when you have the data, but for novel mathematics, it's naturally data scarce. And another challenge is the action space. If you compare mathematics with playing Go, a big difference is the action space in Go is large, but it's finite because the board is 19 by 19, so the action space is smaller than 19 by 19. But the action space in mathematics, that's the potential thing you can do when proving the theorem, is infinite. And if the space is infinite, it's very hard to cover the space uniformly by human-created datasets. Also, it's very difficult for the model to explore by itself and use reinforcement learning. So then how are we going to deal with the action space? So here's another project that we want to like tame the action space, improving theorems. And here we focus on not general theorems, but a particular form of theorems, that's inequalities. So here's an example, like given ABC, three real numbers, you want to prove this inequality. And one thing very good about inequality is the action space here is relatively well understood. And in this project, we will use our understanding of this action space to try to make it manageable. So first, before we try our method, we give the problem to O1 directly, show them the inequality and ask them to prove it. And we manually check the results, and we find out the performance is pretty bad. We tried 20 problems, and O1 proved none of them. But O3 or DeepSeek R1 can prove 3 or 4 of them. Whereas, well, a gold medal level human can prove at least 16. So then our method is we want to study the action space in this particular problem. We categorize the action space into two types. One is called scaling. Scaling is when proving an inequality, you use an existing inequality to try to scale a term in the current inequality. Like this is example. On the left-hand side of this term, it can match with the Cauchy-Schwarz inequality. And you apply Cauchy-Schwarz, it will scale the left-hand side to the right-hand side. So that's scaling. A good thing about scaling is the action space for scaling is not infinite, it's finite. That's because there is a finite number of lemmas, like Cauchy-Schwarz or AMGM, and for each lemma, there is only a finite number of ways to apply it to a current statement. So the scaling is finite. But then we have another class of tactics called rewriting. So rewriting is you have a current formula and you can rewrite it into another formula that's equivalent. And unfortunately, the number of ways you can potentially rewrite a formula is infinite. Like you have x, you can do x plus 1 minus 1, x plus 1 minus 1, plus 1 minus 1. So there's an infinite number of ways to do it. And here's what we do is we give the current formula to the language model and ask it to propose the top 10 or top 20 potentially useful rewrites. So then we have scaling and rewriting, and we combine them in a proof search loop. So in every step, we have a symbolic algorithm that's enumerating the number of scaling tactics because it's finite. And we have a neural algorithm that's doing the rewriting, and we combine the scaling and rewriting uh, to put it into a proof search algorithm. So here's an example. You like in the first step, you scale with Cauchy-Schwarz, so your goal becomes this, and then you scale with AMGM becomes this, and then you use language models to do the rewriting. It becomes a squared times plus b squared plus c squared, smaller than or equal to a squared plus b squared plus c squared, which is trivial. Then your inequality is proved. And we evaluate this method on the same 20 problem, and it can solve 16 of them. And we also collected a larger data set of inequalities. So here we have 3 data sets collected from different sources. Each row is the data set, and each column is a method. We compare our method, that's the second last column called lips, with a few baselines. We compare with both neural baselines and symbolic baselines. Here, the symbolic baseline is actually doing pretty good, but lips is still better. And some interesting finding here is that lips can find novel proofs that's different from human written proofs. Like here's an example from Ivan Chen, who is a ML coach. He wrote a book, and he mentioned, okay, for this problem, AMGM alone is hopeless here, but we find that the proof found by Lips uses only AMGM in combination with very clever rewriting. And the takeaway in this project is theorem proving is challenging. Part of the reason is you have an infinite action space, and the key is how to efficiently explore the action space. And if you are focusing on a specialized mathematical domain, like inequality or other domains that you are familiar with, maybe you have insights on what actions make sense. You have some knowledge of this action space. It's not purely uniform. And you can use that knowledge to design a prover that's by far more efficient than a generic next step generation prover. Of course, the open problem here is, are we going to design a specialized prover for each domain, or is there really a way to have some insights that's generalizing across different domains? So that's the part that concludes the part about theorem proving, and we will be talking about auto formalization next. But I want to pause for a few seconds if you have any questions.
So in the so there was this algorithm that you had developed where you were doing this theorem search from the set of possibilities that you have as axioms, right? So over there, you can also do some type checking of the theorems that you need per se, right? Like not exactly do an encoding to the cosine vectors and have a distance between 2 different cosines.
Are you talking about this step? The step on this
Just
or
go a
the
little
previous
further.
one? Like
Yeah.
which lemmas are
Yeah,
useful?
here. So you were all the accessible premises that you had. So you
Mhm.
were all encoding them into the vector forms, and then you were doing the distance between these two needed
Yeah.
vector and haha. So you could also do some type checking with the so you would have an understanding of what premise that you want to prove, and you could prune your search space on the set of theorems that you have on the only possible ones, and then do this particular encoding and then see the list ones.
Yeah, I think it's definitely possible to have some type checking or any other symbolic algorithm as a
As
they can say
also
as a filter. There are things that should be excluded.
hmm.
We don't do that here,
Okay,
but
okay.
I think that's possible. Although that's also quite non-trivial because there are different ways
In which
a,
the
a lemma
uh,
can be used in the tactic.
okay, I understand.
Okay, then let's go to
Quick question. So it seems like you're exploring the action space in a very step-by-step way. Like for
Yes.
example, you're rewriting all the inequalities. And humans don't really do that. They have like hunches. Like what's the current research on AI developing a hunch that is kind of fuzzy, but you can validate or invalidate it?
Mhm. Uh, I think the most generic way of doing that is potentially like before generating the next step, your language models can kind of think. Think here just means it outputs some chain of thoughts. So in this chain of thought, maybe it will say, okay, here we are doing this, and the next step, so I think the next direction should be that, and then it conditioning on this output to generate the next tactic. Although there are certainly no guarantee that, so this is more like an emergent behavior. It's not hard-coded into the dataset, so it's not super reliable.
Mhm.
Mhm. Okay, then probably going to talk about auto-formalization. That's we have informal math, and we want to translate automatically using language models to formal math. And here there are a few things we can translate. Like on the left, we're using this example. Like on the left, there is a theorem. There exists an infinite number of primes, and there's a proof of this theorem. On the right is the formal version of this theorem and its proof. And here in auto-formalization, one thing we can auto-formalize is the statement. So we can translate the informal statement to the formal statement. And another thing we want to auto-formalize is the proof, translating from informal proof to formal proof. And I will discuss separately because these two subtasks, they have different challenges. So for example, for statements, so let's forget about proofs for now. Um, the challenge in auto-formalizing statement is you don't know how to evaluate. Like for this example, here is the correct translation, but it's not the only correct translation. If you look at it, it says for any natural number n, there exists a natural number p. P is greater than or equal to n, and p is a prime number, which is correct. But you can write in another way. Like, for example, if I change p greater than or equal to n to p strictly greater than n, it's the same. The semantic is the same. And I can even require n is also a prime number. Like for any prime number, I can find an even larger prime number. So all those alternatives are equally correct. And the problem is then if you machine generate one of them and it's different from the ground truth, how do you even check it's correct or not? I think here it's kind of like a program equivalence checking. You want to check whether they're semantically or logically equivalent. But this is very difficult to do. And you can, of course, using humans to tell you whether it's correct. But humans are very expensive, and it's also not super reliable in the as an evaluation. So that's the challenge in auto-formalizing theorem statement. And how about proofs? Proofs have a different challenge. That's the informal proofs written by humans, they often have a lot of gaps. Some are explicit gaps, like mathematicians often say, okay, we have two cases. I'm going to discuss case one, and case two is similar, and it's left to the reader. So that's kind of explicit gap. And there is also gap that's implicit, which we will talk more later. But regardless of what gap, like explicit gap or implicit gap, when you translate the proof into formal proof, it must be gap-free for computers, for Lin to check it. That means your model should fill in all the gaps, which can be quite difficult. And we talked about two challenges. For statements, you don't know how to evaluate. For proofs, you have to fill in the gaps. So in this project, we want to address these two problems. But that sounds too ambitious. So we are going to address it in a very limited setting, in a very limited domain. And one thing we learned in this project is that since intractable in general can be made tractable if you have a very specific domain. And here the domain we pick is Euclidean geometry. That's because it's been used for testing humans for 2000 years, and also recently it raised a lot of attention in AI, like the alpha geometry from DeepMind. And here in this project, we collect a benchmark called Lin Euclid. It's not for solving geometry problem, but it's for auto-formalizing Euclidean geometry problem. This benchmark has 48 theorems and proofs from formalized from Euclid's elements, and 125 theorems and proofs from another dataset. So let's see one example from this benchmark. So here is Euclid's elements proposition 1. We have the informal theorem and the proof from the original text of Euclid's elements, or translated into English. And then it also comes with a diagram. And then when constructing the benchmark, we manually formalize it into Lin. So we have a theorem statement in Lin, and we have the proof in Lin. Actually, this process is very interesting because I believe this is the first faithful translation into Lin of like Euclid's proofs. And actually, in this process, we find a few bugs in Euclid's proofs. I'm going to show one interesting example. So this is proposition 24 in book 1. The statement says you have two triangles, ABC, DEF, and you know AB equals to DE, AC equals to DF. So that's red equals to red, blue equals to blue. And you know the angle A is bigger than angle D. And you want to prove BC is longer than EF. So that's Euclid's theorem statement. And so that's it's not too difficult, and I'm going to go through the proof written by Euclid. Step 1, you move the big triangle to overlap with the small triangle. So AB will overlap with DE, and C is moved to G. And then you connect G and F. And now the problem is reduced to proving EG greater than EF. It's good because EG and EF are now in the same triangle. And there is a previous lemma in this book says in the same triangle, a bigger angle corresponds to a longer edge. So then we only have to prove this EFG, this big angle, is bigger than this EGF. That's a small angle. And to prove that the bigger angle is bigger than the small angle, we can use another angle as the middle point. So we know that AC equals to DG and equals to DF. So DG equals to DF. Then a previous lemma told us DGF, the angle DGF equals to the angle DFG. So then you can use DGF and DFG as the angle in the middle, because the big angle is bigger than DGF. Oh, sorry, the big angle is bigger than DFG, and DFG is bigger than DGF, and DGF is bigger than the small angle. Then that's done. So I want to ask anyone disagree with this proof. Okay, maybe no. Then this proof is correct, but it only works for this diagram. So if the two triangles look like this instead of this, it no longer works. So to show why it no longer works, let me try to replay the proof. Step 1, move the two triangles so that they overlap. Step 2, connect G and F. And now you notice there's a angle alpha, that's the angle in the middle. And you want to prove that the big angle X is bigger than the smaller angle Y. But the problem is that now alpha is outside X and Y. It cannot be used as the angle in the middle. Whereas in the previous example, alpha is the DFG and DGF. They are inside X and Y. So then proof no longer works, we have to fix it. And fortunately, we were able to fix it. And our fixed version is you first notice the DGE, that's alpha plus y. Alpha plus y, it's an inner angle, so that's smaller than 2 pi. And you also notice the DFE. DFE is 2 pi minus alpha minus x. It's also an inner angle, so it's smaller than 2 pi. And then you add these inequalities together, and things will cancel out, and then you get x greater than y. So this is a bit more challenging than Euclid's original proofs. So what's happening here is this theorem has at least 2 cases, and Euclid only improved the simpler case, and he omitted the more challenging case.
So Kaiyu, I have a question. So this is a question on the theorem prover's abilities. So is it able to give you a counterexample to this theorem? Once you write the proof, once you formalize it. So could it be giving you this picture of the counter triangles and all that?
So currently the theorem provers it does not have diagrams at all. So
I know, but
yeah,
like
and
some encoding of the basically the triangles.
it's possible for it to give you a counterexample. I think what more likely happen is it just cannot prove the theorem. Because
Okay.
or cannot prove the theorem without
Conclusive.
explicitly discussing the other case.
Okay.
So that's the data set. It's probably not related to the model. And then we are going to go back to the model side. So what this data set enables us is we can evaluate the model. So and for evaluation, we need equivalence checking between 2 theorems. So if we have a ground truth theorem and you have an auto-formalized theorem that's predicted by the model, so what we do is we use SMT solver to try to prove their equivalence, to try to prove they imply each other. And here is actually more tricky than it sounds because under this definition, any 2 true statements imply each other. The two they can be totally unrelated as long as they are both true. Uh, and the thing is, SMT solver is not powerful enough. It can only improve implications that are obvious. So if these 2 statements are completely different, very likely SMT solvers will not be able to prove it. So here, we're actually relying on the imperfectness of SMT solver to empirically define equivalence. So it's not a theoretical argument. It's more like a empirical setup. And so that's how we check the statement's equivalency. And the other thing I haven't covered in this here is the gaps in the proofs. And so reason we choose Euclidean geometry is in Euclidean geometry, there is a very well understood kind of gaps that's called diagrammatical reasoning gaps. I'm going to show it in an example. So this is proposition 1 in Euclid's Elements, book 1. That's given 2 different points, A and B. You can construct an equilateral triangle. And here is how Euclid did it. First, you draw a circle centered at A and passes B. Then you draw a circle centered at B and passes A. And then you take the intersection as C, and you connect everything. And that's an equilateral triangle. Anyone disagree with this proof? The problem is we don't know whether C exists. Euclid didn't prove C exists. They didn't prove these 2 circles have an intersection. And a more important problem is actually it's not provable. It's not like Euclid omitted this proof because this is proposition 1. There's no lemmas before it. So if you want to prove these statements, you can only use axioms. And I mean, Euclid have a few axioms at the beginning. And if you try to use it, you will find that there's no way to prove C actually exists. So here is, but people also don't bother to prove it because it's just so obvious in the diagram. But the problem is if you want to formalize this in Ling, Ling does not know what is obvious in the diagram. So you kind of you need a computational definition of obviousness in the diagram. And So way to solve it is you have, well, this is actually proposed by prior work by some philosophers. They kind of model obvious in the diagram as like kind of you have a set of unspoken axioms. And a fact is obvious in the diagram if it can be derived by those like diagrammatical axioms or unspoken axioms. And we implement this set of axioms in Ling and a automated prover to derive the consequences of those axioms. That's also backed by SMT solver. So let's put it together. So you have a benchmark, you have informal proofs, you have diagrams, and you have the formal statements. And so your model generates auto-formalized statements. And in order to evaluate these model-generated statements, you use SMT solver to prove their equivalence. And your model also generates a proof. And you give this proof to Ling. Ling will identify a bunch of gaps. And then for each gap, you use SMT solver to see if the gap is obvious in the diagram. And if all of them are obvious, then you accept this as a correct proof. So that's the overall way to evaluate auto-formalization using our benchmark. And we also, so once we have a benchmark and evaluation, we also did some experiments. And here, here the models are a bit outdated. So it's GPT-4, very early version of GPT-4 when it was only when released for a few months. And here the y-axis is the success rate, and x-axis is the number of examples you show to the model. So as you can see, you can show more examples and it will get higher, but still it's quite challenging because the success rate is only around 20%. And the takeaway in this project is we have two challenges in auto-formalization. For statements, we don't know how to evaluate, and for proofs, we have to fill in the gaps. And in this particular project, we show that if you have a domain, then using insights from this domain, you can address both problems using automated reasoning. Still, the open problem is how do you generalize across to a different domain? Cool. I think that's what I'm going to discuss for today's talk. And thanks for coming, and happy to take questions.
Kaiyu, thank you so much. That was terrific. I think we'll have a lot of questions, but maybe I'll just start us off. There's a bunch of people here who do software verification, which is like sort of subtly different from mathematical verification. And I'm just curious how well you think the existing mathematical verification work is going to extend to a software domain when people start taking that problem seriously.
I think this extension is people always want to do, but we see a few challenges. So one difference is in software, there are more customized definitions. Like every function, you can think of it as a new definition. Whereas in mathematics, you also define a few things, but the number of unique definitions is relatively small. Like you define real number, then you can use it everywhere. And the other, in terms of proofs, a big difference is software verification uses induction a lot. Whereas induction is also used in mathematics, but it's not nearly as prevalent. And then, of course, there are also tons of engineering challenges. Like how do you synthesize the data? How do you model a real, just manage the specification of the software? I think there are a lot of gaps, although people think that's an area people are actively working on.
So Kaiyu, I have a question. So when we are talking about, say, advanced mathematics and not being able to have a hold on the action space and all that, and then you went on to talk about, say, these inequalities. So in the domain of inequalities and all that, and there is a set of action spaces that you could sort of list over and like be able to sort of generate these things. So do you think like say the larger question can be like you can look into say these small sub or different domains of maths, and perhaps they would have more finite action spaces, and then you can compose all of them in I think humans compose all of them very in ingenious ways, and that's the creativity and art in mathematics per se. And I'm not sure if LLMs will have this emergent behavior of being able to like from each of these domains guess a new sort of action which is unique and different from each of these particular say actions that were taken in say algebraic geometry and say number theory, something like that, and be able to match together something new. So do you think that is like a way forward for the to get towards the larger holy grail of trying to do research level mathematics and all, or perhaps all P not equals to NP sort of questions?
I think that's a really good question. Actually, I'm not sure I'm going to have a good answer because I'm not a mathematician. But I believe it depends a lot on the particular mathematics domain. Like there are domains that are relatively closed, and so in the sense that you have a relatively fixed set of tactics. That's especially common in competition math. Like in IMO, you always have one geometry problem, one combinatorics problem, and one this algebra problem or whatever. And you have like for geometry problem, it's the tactics is very, very close. You like uh, draw a new line and then you like deduce some properties about this new line. And there are also relatively niche areas in mathematics.
Yeah.
Maybe some mathematicians only care about graphs, and then in this particular domain, like it's also relatively closed. But there are also mathematics domains that are relatively open in the sense that you can even borrow tactics from a seemingly irrelevant space. Like you can combine analysis with geometry with algebra. Then it will be very challenging to design an action space without limiting our the expressiveness of our methods.
Okay.
I think it's
So
interesting that.
we hit a Godelian deadlock sort of a thing. So okay, sorry, Max, I'll just take this
Oh,
up.
you're good.
Yeah. So so from the perspective of mathematical logic, so the area of Euclidean geometry is formalizable. So you can have a decidable. I mean, like whatever theorems you write, you would be able to like have a Turing machine go at it and solve the problem. Okay, like decidably. And so when you go to number theory with, say, the expressive powers that it has, you are not able to. So this is Gödel's theorem that you are not able to sort of always prove a true statement. So you have to use it as an axiom sort of thing. So this is in the realm of, say, formalization of mathematics at a larger logical level. But like, say, at the level of, say, AI tools at its current development, okay, what are the kind of theorems do you think it will not be able to sort of have a proof for or something like this?
I think it's in principle there is always well you can always represent the theorems and proofs in Ling. That's because Ling is in principle, as long as you have first order logic plus CFC set theory, you can represent anything. And the Ling is a superset of that. But in practice, there's a matter of like some mathematics are much more difficult to code than other mathematics. And I think that's pretty much a engineering and empirical question. So that we don't know.
Okay, thank you.
Wasn't there something where like a theorem prover isn't able to prove itself true?
That's not well. Yes and no. For example, Ling. In Ling, there is there's a very small trusted kernel that's for proof checking. That's the maybe like 1 or 2 thousand lines of code, and there are other other functions. So the assumption is that we will use a lot of humans to make sure the trusted kernel is correct. But the outside functions, they can be incorrect. That's totally fine because everything will be checked by the kernel by the end. And then people are also trying to check the kernel using kind of like external checker. So you can write maybe a third-party checker for a kernel checker for Ling. So that you can check the proof independently by multiple checkers. But I'm not aware of like proving itself correct. But I guess Clock have something like that. But I don't know the detail of that project. like proving the correctness of cock in cock something. I think unfortunately I have to go because I have another.
Oh, no worries.
But I mean,
Kaiyu, thank you so much for talking to us. We really appreciate your time.
Thank you
yeah,
very much.
thank you for inviting me. And I mean, if you have questions, we can always talk offline.
Okay.
Thank you.
Adios. Thank you, Kaiyu.